Okay, good afternoon, and so I thank the organizers for continuing to organize this very nice meeting, giving us an opportunity to meet and discuss various things. And so today I'll be talking about some work in progress. So this is not finished work, and I'll be very happy to get some feedback from you regarding this work. So, so the topic is. So we are interested to study residual stress. I'll tell you what residual stress is in athermal amorphous materials. And this is somewhat related to what Sanjib was telling about. So the work is done by Vishwas, who some of you know, is currently a postdoc in Grenoble with Kristen Martens. And so this is a combination of mesoscale and microscopic numerical simulations, and I'll explain in details what we're doing. So as Sanjib discussed, that we are interested in amorphous materials which are in this disordered jam state. For example, his interest was in athermal systems, which is also my interest. But this kind of athermal disordered system, the jam systems can be obtained either via the temperature route or via the density route. And the point here is that all these jam disordered states have similar properties, and this is what people have been studying under different situations for the last 2 decades or so. So one interesting feature of these jam disordered systems is that they have a very rough landscape. That is, there are multiple minima which can be occupied by these disordered states at very low temperatures, and this has a consequence to this kind of residual stress behavior that we are interested in. And of course, as Sanjib mentioned, that there is a threshold, a yield threshold, crossing which the system unjams and starts flowing. So what is residual stress and why are we interested? So residual stress, as Wikipedia describes, are stresses that remain in a solid material after the work that you have been doing on the system is removed. Okay, so suppose you are heating the system and then you suddenly cool the system, then whatever stress is remaining in that system is the residual stress. Okay. So the classic example are these Prince Rupert drops, so which are like glass tadpoles, which have been formed by if you just quickly quench glass into liquid water or cool water, and then these very slender structures are very difficult to break because of the stress that is locked inside the system, and only they can break if you hammer at the tip of the tadpole. So the Gorilla Glass, which all of us use in the iPhones, this is also a consequence of this residual stress that is encoded into the system via some chemical process and so on. So it is of engineering significance, as you can see, and it is useful sometimes to make systems tougher, more plastic and so on, but it can also be harmful because the fractures can emanate from these residual stresses and so on. So there are various routes to reach, to have this kind of residual stresses. It can be some thermal treatment by the heating and cooling process, by some chemical, by if you remove some of the ions and put different kind of ions like calcium and sodium and so on, which is done in Gorilla glasses, for example, or you can do some microscopic synthetic process by which you can include the stress inside the system. So the important question is, can we tune it, and can we make it useful? And this we would like to understand from very simple systems. So what I told you earlier are more hard glasses or window glasses, those kind of things. But these kind of residual stresses are also present in soft glasses. So this became a topic of interest in recent times because of 2 studies that happened. So one was a combined study of MD simulations, experiments, and some mode coupling calculations, where they showed that if you are at temperatures above the glass transition temperature, and there the protocol is that you are shearing the system at some temperature, and then you switch off that shear, and then you ask what happens to the system after you switch off the shear. So if you are in a liquid and if you switch off the shear, whatever the stress that was being generated in the system because of the shear, that is completely dissipated out by the thermal equilibration process. On the other hand, if you are in the glassy regime, then the stress no longer gets relaxed, and what you have is an aging kind of process that eventually you never reach over the experimental time scales, you never reach a fixed stress value. The system continues to age because of the thermal aging process. On the other hand, if you are at thermal systems, there if you do the switch off of the shear, you see that the system gets locked into some stress value. And this stress value depends upon, as they showed in this scaling plot, it depends on the stress at which you had switched off the shear. So there is a relation, there's a correlation between the initial stress value and the locked-in stress value. Okay, so then we would like to understand from a microscopic and a meso approach how the spatiotemporal emergence of residual stress happens, what is the spatial structure, what are the consequences, and so on. So the simple model system that we have for the microscopic simulations is just a collection of soft spheres, and this is that under athermal conditions, that is, temperature is not important. We do some finite shear of the system, and then we switch off the shear and see how the system responds to that. So as Sankan showed, these kind of systems have a very simple flow behavior. So these have yield stress followed by a shear rate dependent regime. So these systems, this model system has the yield stress that we are looking for. Okay, so what happens after you switch off the shear? So the system, certain shear rate has been applied in the system is flowing, so there is some transient state, let's forget it for now. So there is some steady state shear stress that is generated in the system because of the shear, and as you switch off the shear, the system relaxes and it gets locked into some residual stress. Okay, so now if you do it at different shear rates, what you see is that the residual stress depends on the shear rate that at which it was flowing. The larger the shear rate, the lower the residual stress that you achieve. Okay, and so one can then plot the residual stress as a function of the applied shear rate, and you can see that there is a dependence of the residual stress on the shear rate. There is a power law form, and as your initial stress becomes closer and closer to the yield threshold, the residual stress also becomes closer and closer to the yield threshold. Or in other words, if you're switching off the shear in a system which is very close to the yield threshold, it goes and resides in a state which is in one of the local minimum in the potential energy landscape, which is near wherever it was flowing. On the other hand, if you think of the potential energy landscape in the case of the large shear rate, because of the large inertia that the system was flowing in, it basically rolls down that landscape and reaches a lower energy state. We'll see how that process and so on. Okay. The other interesting thing that we observe is that if you re-shear the system, then we see something that is reproducible. So basically, this is the system at a certain residual stress. You re-shear the system, you see this response like this. You again switch off, there's a residual stress, you switch on and switch off. So the important point here is that not only you achieve the same flowing shear rate, but also the response becomes reproducible. So given a residual stress, there is a unique response that one can assign to it. And one would like to understand how this unique response is coming about. We don't have the answer yet, but this is something we would like to understand. So here what we can see is that there is some steady state behavior, it is reproducible, and we would like to do some statistical analysis of this. Unfortunately, microscopic simulations have limited scope in scale and time, so we would like to do something better. So that is where meso models come in. I don't know whether Alberto Rosfo talked about meso models yesterday, but he's an expert in this. So in meso model, you are looking at some post-grain variables, in this case the stress. So there you are looking at the time evolution of the stress of a single block, of an array of blocks, and the rules are very simple. So you have applied an external drive, which is the shear rate, the system is flowing, and then this single unit, if the local stress crosses some yield threshold, it topples. It's very simple, similar to a sandpile model, except that now the stress gets redistributed via this kernel, which has this long range form because of the elastic interactions and so on. So you continue with this iterative scheme, and then you see, and these kind of models have been able to reproduce steady state flow behavior very well. And you can read this in this RMP article. So a system is deemed to be active if it has toppled, and after some time, there's a sense of time here, the system again goes back to this inactive state and again starts loading and so on. So in the case of the residual stress problem, what we'll do is we'll switch off this term and see how the activity evolves as a function of time. So just to show you, the macroscopic curves that we get are very similar to the microscopic simulations. So depending on the initial stress where you are deciding, the residual stress also also depends on it in a similar power law behavior. The exponents are slightly different. We are not comparing similar models. It's just the same qualitative scenario that we are reproducing via these mesoscopic models. Okay. So what I told you earlier is that we can monitor the activity at each block within this system. So at very small shear rate, there are very few active zones. As you increase the shear rates, the number of active zones go on increasing. This is in the steady state, so we are just showing you a snapshot in the steady state. So then you can switch off the shear and see where the system leads to. So these are the residual stress states. So what you can see that there is a lot of texture, but we haven't analyzed this texture yet, which you would like to understand because this is where the information is encoded for subsequent response of the system. So what we have done is we have plotted the, yeah, I'll just one more slide. So what we have done is we have seen the difference in stress locally between the initial state and the final state. So what you can see is that if your drive is very slow, then the stress relaxation is very local. It very quickly goes to the nearest minimum that is available to it, okay? On the other hand, if your shear is large, if there is a lot of activity, it is driving the system far away, and you have a lot of stress relaxation that is happening within the system. So we now understand that how this residual stress is getting locked into the system via the activity that was there in the flowing state, okay? So I'll skip this for the moment, say for the sake of time. One can measure what are the local yield thresholds in the system, and we see some dependence on the residual stress states and so on. So the last slide is basically about now that you are switching on the shear. Suppose you have a system residing in different residual states, stress states, then you impose a shear again, how do they respond? So what we see is, of course, that eventually they have the same steady state at long times, but the transients are very different. So if you are at a system which has a large residual stress, it very quickly goes into the flowing steady state. On the other hand, if you are in a low-lying residual stress state, then it takes longer to reach the steady state flow. So you'd like to understand what is encoded into these states, as I showed you earlier, that would allow us to make this kind of connection between the residual stress states and the flowing states. So this is a work in progress, so I'd like to get your feedback on this. So these are the conclusions. We are studying the emergence of residual stress in disordered thermal systems by this combined method of microscopic and mesoscale analysis. And we show that flow history determines local relaxation and thus residual stress. And we can, the residual stress magnitude can determine subsequent response and so on. Thank you.
Let's thank Pinaki. So any question?
Yes, and this is something that we are debating. Where is this coming from? And I'm not sure the treatment that you had done earlier, where you are shifting the distribution, it helps here in this case or not, because the distributions are very similar for the different residual stress states. So there's something else in the rules that you have to put in order to get the peak. So this we are trying to figure out.
Okay, I have
Yes.
yeah, so that residual stress that you residual stress that you mentioned, so does it go to a steady state, or it's still a slow decaying?
So in the case of a thermal system, it's a locked in state. There is no dynamics at all. For the case of thermal systems, there is an aging process, therefore the residual stress will continue to change.
Okay.
That's an interesting point. I mean, we can discuss it later. Yes. Thank you.